Today we're going to finish up our discussion on the fluid states, the third day here. And by the end of the day, you should be able to compare and contrast liquids and gases, describe how cohesive and adhesive forces cause surface tension and capillary action, and then use the kinetic theory to describe evaporation and condensation. I've got a bell ringer here for you to do. And if you would work on that bell ringer, when you decide you're done, go ahead and unpause the video and you can see the answer. So what is the apparent weight of a rock if it's submerged? Well, if you've got a rock submerged in water, here's my rock, the forces acting on that rock are the weight going down. We know if it's submerged, there's a buoyant force going up, and then the difference between those two would be the apparent weight. So what we are solving for is this force right here. That would be the upward force on a scale if you were sitting on one. So these net forces would have to be 0 and such. Well, my weight, we know is 85 newtons. So all I really need to do is find the buoyant force. And once I know the buoyant force, then I can figure out my apparent weight. The equation for buoyant force, remember, is weight density of the liquid times volume times g. Well, in this case, my fluid is water, and it's got a weight density of 1,000 kilograms per meter cubed. It was nice they gave me my volume in meters cubed, so I don't have to worry about converting, but quite often you'll have to convert this unit to be the same as the density units. Notice now my meters cubed cancel out, and then G is just 9.8 meters per second squared. So we're left with, when you multiply all this, units of kilogram meters per second squared, which is a unit of force, a newton. So 1,000 times 0.0044 times 9.8 would give me a buoyant force of 43 newtons. Now that's not the answer, that's the buoyant force. The apparent force, right here, F apparent, would be found by taking the force of gravity, which we know, minus our buoyant force. So the force of gravity here was 85 newtons minus the buoyant force of 43, and we would get an apparent weight of 42 newtons. So we know our buoyant force, we calculated that to be 43 newtons. Our apparent weight would be 42 newtons. And hopefully that makes sense because, again, the net forces have to equal 0. So you've got 85 newtons up and 85 newtons down. So it would definitely appear to weigh less than it did in the air. So let's get to our notes then. Liquids versus gases. You know a lot about this already from chemistry. So just some main definitions of liquids and gases. Liquids, we know, have a definite volume, which means if you pour them 200 milliliters from one beaker, to a flask, to a test tube, the volume stays the same. They're incompressible, which tells me something about how close the particles are. And the volume is due mostly to the particles, not a whole lot of space in between. Gases have indefinite volume, so their volume is going to change based on whatever container they're in. They're compressible because the volume is mostly empty space. If you look at the diagram here, this has all three. Gases, we said, are here your atoms or molecules are flying around, mostly empty space. Actually, we'd assume the size of the molecule is even less compared to the container. So they're free to fly around everywhere. Liquids, on the other hand, their particles are very, very close together. Now, they're not bound tightly, so they're able to roll around and flow, but the fact that the particles are right next to each other doesn't allow for any compression. Solids, of course, the particles are right next to each other and rigid, so they don't change their volume, they don't change their shape, and they can't compress either. Cohesion is just a force of attraction between similar substances. And this would be an electromagnetic force. But cohesive force, water will attract other water molecules due to cohesion. Surface tension is defined as the tendency of a surface of a liquid to contract to the smallest area. And again, we talked about this term in chemistry. The main reason this happens is because of the cohesive forces, the attraction between similar substances. However, it's really the attraction, or the fact that there's a net downward attraction only at the surface of a molecule. So if we look at these diagrams, if this is a beaker of water, every water molecule below the surface is attracted upward. You've got an upward force, downward force, left force, right force, angles here. And notice they all are equal and opposite. They all cancel out. If you look at the surface molecule, this guy can go left to right. This guy will actually, the arrows aren't drawn, but it can be attracted downward, and it can be attracted this way. But you'll notice there's nothing up here. So the net force acting on the molecules at the surface would be a net downward force. There's nothing pulling it back up, and because of this, it kind of acts like there's a film, a thin film, on the layer of different liquids. Now, there really isn't, but kind of envision it kind of like that soup skin you get with tomato soup, where stuff is kind of thicker on there. That's kind of how surface tension acts or behaves like. It's because of this that you can do things such as balancing a piece of metal, a paperclip, on water. We know that aluminum has a density much greater than that of water, but if you're careful and don't break through the top surface, it'll actually float. So if you want to try this, grab yourself a glass of water, grab a paperclip, and take your paperclip and make sure when you're putting it on, you just slide it on this way, If you actually insert it more like this and it breaks that top layer, it'll fall to the bottom, which is kind of fun to see as well, but we'll let you double check and see both of those things. If you look in your book on page 323, you've got a really nice picture of a drop of mercury, alcohol, and water. And you'll notice the mercury just kind of balls up together into a sphere. That's because it has really, really strong cohesive forces. It wants to keep it together. And obviously the alcohol on the far right is the weakest. Water's in the middle, pretty strong too. So cohesion is a force of attraction between similar substances. Adhesion is a force of attraction that acts between particles of different substances. You've heard the term something adheres to something, it sticks to something. Well, one thing sticks to something else because there's an attraction from one type of particle to another. And this is also an electromagnetic force. When we get to class, we'll show you some examples of adhesion and cohesion. And we'll even show you some examples of capillary action. That's our next thing. Capillary action is the fact that liquids will rise in narrow tubes because of the adhesive forces between the liquid and the tube. If the tube is made out of glass, you have attraction between water and the glass, possibly, and it's going to cause that liquid to rise. It works for all types of things. Every different substance has different adhesive forces, so the amount it would go up is different, but capillary action is the rise of liquids in narrow tubes due to adhesion. And this continues until the weight of the fluid equals the adhesive forces. So obviously, if I've got this narrow tube over here, and it's sticking that in a beaker of water, this is all water, some of that water will go up into this tube and it will actually rise up into that tube a little bit, maybe like so. Well, the force is acting on this water. We know there is a weight pulling it downward, and the adhesive force is the water attracting the liquid that is trying to pull it upward, your adhesive force. And this can continue to climb until these forces are balanced. If you've equaled the weight, you can't go any further. Which leads to some interesting things. Obviously, the wider the tube, the lower it can rise before the weight is equal to the adhesive force. So this is trying to show you all these different width tubes. So here's how wide the first tube is. There's the next tube. There's the next tube. A little narrower. Narrower. And you can see as it gets narrower and narrower, the amount of liquid goes up. So the volume is probably the same because the volume, same volume would give you the same weight, and you have the same adhesion because of the liquid going into the glass. But obviously the wider the tube, the less high it can go to have equal the same weight. Evaporation and condensation. These are just changes of states. Evaporation is the escape of particles from a liquid to a gas. This happens spontaneously. We know that molecules are continually moving around. If a molecule has enough energy to break free from the liquid state, it's going to turn into the gas. So the most energetic molecules are the ones that are leaving. And if you lose all your high energy molecules, you're left with less energy, and that's why evaporation really is a cooling process. You're left with less energetic molecules. It takes energy to actually go from a liquid to a gas, so energy is absorbed. You have less energy from the surroundings around it because it's taken some of that energy. Things that evaporate easily we describe as being volatile. I assume you can think of some volatile liquids. Gasoline is a very volatile liquid. Acetone is a very volatile liquid. That's why we use it in organic chemistry to clean glassware. You mix it in there and pour it away, and it evaporates before you can get spots on your glassware. The opposite of evaporation is condensation. And it's changing from a gas back to a liquid. So sitting in a nice hot summer day on your deck, enjoying a cold can of Coca-Cola Classic, you'll notice that the can all of a sudden starts to sweat. That is just condensation forming. There's moisture in the air. And as that moisture runs into the cold can, it loses energy, cools back down, and turns into a liquid. And that's why you get the water vapor forming on the outside of your can. Lastly is the last state of plasma. And just think of plasma the same as a gas. Plasmas are gas-like substances. They have indefinite volume. They're compressible, made up mostly of empty space. The only difference between plasmas and gases are they're made up of charged particles. So you have negatively charged electrons and positively charged ions to make up plasmas. So if you take a gas, add enough energy to rip apart the molecule so you end up with a charged particles, then you've turned your gas into a plasma. We'll look at section 13.2 tomorrow.